Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is drafting wave. Okay. So, drafting wave is basically the irregularity generated during drafting, and in the roller drafting the fibers, the floating fibers move either at the speed of the fibers connected with the back roller nip, that is at the speed of back roller, or at the speed of the front roller. So, during this movement, so the floating fibers, they have the erratic movement. Suddenly it changes movement from the front roller to the back roller to the front roller speed. So, during this stage, so it forms the thick thin places, and it has been observed during the drafting, whatever the thick thin places observed, so they form a certain wavy pattern. So, the certain wavelength is there. So, that is why it is called the drafting wave. Drafting wave is basically generated due to the wrong setting, roller setting, and also if there is a short fiber content are more. So, chances of drafting wave generation will be more. So, let us see the drafting situation here. Here if we see here, so if the drafting zone setting is such that the trailing ends of the longer extent are released just as their leading ends are nipped. So, this is the when the leading ends, when the leading end is nipped, the trailing end will be released. So, that basically that is the thing, and then spewing does not occur. The spewing occur when the both the ends are gripped by the both the front and back rollers. So, if it is the situation when the fibers is gripped by the front roller, this is the front roller and here is the back roller. By that time the fiber is released by the back roller nip. So, then spewing does not occur. However, there will be the fiber extent that are not nipped by either back roller or front roller. So, we have solved one problem of spewing by increasing the roller setting with respect to fiber length, but the main problem will be there will then it is generating the floating fibers. Okay. So, these fibers neither gripped by the front roller nip nor by the back roller nip. So, that these are the floating fiber, and these floating fibers are actually reason for the drafting wave. Now, in ideal drafting case, when we assume that all the fibers are of same length and the roller settings are exactly equal to the fiber length. So, deviation, if we try to come out from that assumption, the situation, the actual cases, the situation will be like this, where we will see the fibers are many fibers, they are actually floating, they are the floating fibers. Now, if you see here, we have in this picture the three fibers are being shown here. So, what are these three fibers? The three types of fibers are, one is the blue fibers. Blue fibers are under the grip of the this back roller, either under the grip of the back roller, or they have not they are actually in connect the in actually in contact with the fibers which are under the grip of the back roller. So, they are effectively moving at the back roller speed, and green fibers are the fast moving fibers. So, these fibers are either in under the grip of the back front roller, or in contact with the fibers which are moving at the speed of the front roller. And in addition to this, there are floating fibers which are shown by the red color here. So, this fiber, they are either in contact of front fibers or in contact of back roller. So, they move at erratically, there is no certain motion. So, they move either at the back roller speed or at the front roller speed. So, or maybe sometime intermediate depending on the contact area. So, these fibers are called floating fibers. Now, on being released by the back roller, these floating fibers will initially travel at the back roller speed, because they are actually in contact with the fibers which are moving at the back roller speed, but subsequently the speed of they will get at the front roller speed. Okay. That will depend on the frictional contact between the surrounding fibers. The surrounding fibers that are nipped by the front roller will try to accelerate the floating fibers, while the surrounding fibers nipped by the back roller nip will tend to slow down the floating fibers. So, the situation that we have discussed. So, here suppose these are the, now let me draw in other color. So, these are the fibers which are under the control of the grip of the front roller. So, this fiber will actually try to pull the floating fiber, red fiber, at the speed of the front roller, but at the same time this blue color fibers will try to pull the fibers, that red fiber, floating fiber, and it will try to move the fiber at the speed of the back roller speed. So, that at which speed it will go, that depends on the contact area, contact force, okay? Surrounding fibers contact force. So, these floating fibers that are close contact with the fibers nipped by the front roller will be pulled as a group. So, this all the fibers, all these fibers, floating fibers, those are in contact with the front roller fibers with the front roller nip will be pulled as a group from those held back by the nip of the back roller. So, they will be pulled in a group and they will reach the front roller nip earlier than the ideal case. So, what happened? These floating fibers, they are moving at a certain speed, and suddenly this fiber will reach at the front roller nip, and start moving at the front roller speed, this group, and in ideal case it should not have happened, they should move at its own depending on their position. So, they should move, but here what happened, this fiber will floating fiber initially was actually moving at the back roller speed. When the contact area with the fibers which are in the front roller nibs control, they, and when they come into contact with the this fiber front roller which are moving at the front roller speed, this fiber as a group will start moving and they will reach to the front roller nib and start moving at the front roller speed earlier than the ideal case. So, this fiber some many of the fibers were supposed to reach at the later stage, but they are reaching at the earlier stage. So, that will actually generate one thick place. So, this is generating a thick place here because of the fact they are reaching to the front roller nib earlier than the where they are supposed to reach and leaving a thin places behind. So, that is what the reason for the generation of the drafting wave. So, the front roller therefore accelerate a thicker group of fibers. So, they will try to accelerate the thicker group of fibers, leaving a thin length momentarily behind. So, they will leave a thin place. So, that it will create a thick place and it will start moving at the front roller speed and a thin place, because the fibers which were supposed to be at this position, they have already reached at the high speed. So, due to the contact point, this is the that is why it is generated a thick thin places. So, we can see here. So, these are the here thick place is generated, and as the more number of fibers has moved to this place. So, at the behind that there will be a less number of fiber, and the fiber in the thin length subsequently reach to the front roller nib, they will reach to the front roller nib, okay, and accelerated to leave a momentarily a thicker place. So, they will get accelerated. So, this thin places they will get accelerated, they will become thicker, and some they will leave some fibers. Now, the interesting thing is that these thin places now these are under control of the front roller nib. Now, this is the front at this front roller nib, these thin places, now they are not able to pull the fibers which are under control of the back roller nib because of the less number of fibers. And what happened, the these fibers which were supposed to move at the front roller speed is not moving at the front roller speed. This is actually effectively moving at the slower speed, and that is why it is accumulating that fiber there and it is becoming a thicker length. So, this thick and thin places is continuing and it is forming a wavelength. So, drafting wavelength, the drafting wave is generated, and in the drafting, see in ideal in the drafting roller. So, this repeats with the with a certain wavelength. Now, many floating fibers move prematurely with the speed of the front roller. So, that they are not supposed to move at that speed, but they are actually moving either by coiring or entanglement. So, by the contact force or by entanglement that are positively gripped by the front roller. So, they have been pulled by the coiring force or by the entanglement. The process is cumulative, and the greater the number of fibers moving forward with the speed of the front rollers, the more floating fibers are likely to be drawn forward prematurely by interfiber cohesion. So, that will give a thick place. In this way, a comparatively large number of floating fibers will be drawn forward. So, there will be large number of floating fibers will be drawn forward by the front roller nib, okay, at one time to give a thick place in the sliver, and this will be followed by a thin corresponding thin place that I have already explained. This is a result of loss of the fibers by premature movement. Okay. So, fibers premature movement takes place, okay, due to the contact point or maybe entanglement. The cycle will give a rise of periodic succession of thick and thin places along the length of material. So, that is the reason for generation of the drafting wave. So, between moments where the fiber leaves the back roller and is directly accelerated by the front roller, it is average speed difference considerably for both the pairs. Okay. So, that is actually average speed differs considerably. So, what happened, this fibers, the average speed will be differing between this speed is not constant. Now, if we see here, it is a fraction of total number of fibers in the cross section in x axis, and here is the distance here, okay, x from the, this is the back roller and here it is a front roller. Now, if you see the back beard, it is a number of fibers will be maximum at the back beard here, and it is gradually reducing. Similarly, in the front beard, the number of fibers at the front beard is here and it is gradually reducing towards that. Now, the floating fibers, if you these are the fibers under control of the back roller, here the fibers are controlled under the front roller. So, these fibers these fibers are moving at the back roller speed. So, and the fibers moving at the front roller speed is this. So, if we see the number of fibers moving at the back roller speed is higher than the number of fibers moving at the front roller speed, because there is a draft. Now, the floating fiber concentration, the number of fibers of the floating fibers, if you can see, floating fibers is increasing, and at the center point closely to the center, the floating fibers are maximum. So, this is because the speed is not constant. So, you can see this is because the fibers will depend on the contact of neighboring fibers. So, we cannot actually expect a constant speed. So, when the fibers are under the control under the nib of the back roller, it moves at constant speed of the back roller speed. But when the fiber is under the control under the nib of the front roller, it moves at the speed of the front roller. But this floating fibers, red color, there is no fixed movement, no consistent movement. Okay, it may move at any speed. So, this is because the fibers, the speed is actually controlled by the contact point of the contact with the neighboring fibers, and there are movements when forces from the frictional contact with the front roller, front beard, cause the fiber to accelerate, and when the large back beard shows the fiber to the near the back roller speed. So, here closer to this at the back roller, the fiber tries to move at the back roller speed. Now, try to see the accelerating point. Where is the accelerating point? Now, you can see here with this picture here. So, here this is the accelerating point here. So, for this fiber, the accelerating point is that this is the front roller nip and front this is back roller nip and here is the front roller nip. Now, this blue fiber will have the accelerating point at this point, okay, and the black fiber has accelerating. So, which is direct suddenly it is coming to the back roller speed. So, it is accelerating point and gradually it is reducing here, because it will take time to reach there. Okay. Similarly, this blue fiber we have seen here. Now, here again this pink fiber, its accelerating point here is maximum accelerating point. Now, it is gradually reducing. Okay. So, it is not getting accelerated, and the floating fibers that we have already seen, the accelerating point is at the maximum at the middle. So, the effect of floating fibers is to produce a successive thick and thin places in the output sliver or output product, where some fibers extent have been drafted in ideal manner. So, floating fibers are basically producing thick thin places, but some of the fibers they follow the ideal manner, but that is again in random fashion. Okay. Now, from this diagram what we can see, the thick and thin variation has a sinusoidal wave and is therefore called as drafting wave. So, this the nature is the sinusoidal. So, that is why it is called drafting wave, and here is the time and the speed of the fiber. So, V1 is the V1 is the speed of the back roller, and V2 is the speed of the front roller, and it gradually increases. Okay. The drafting wave gives an irregularity in addition to the input irregularity. So, input irregularity is already there in the input material, and then drafting wave adds to the irregularity. So, this is the drafting wave. So, what are the factors which actually influence the drafting wave? The amount of draft. So, higher the draft, and there will be the drafting wave will be more. The count of the input material. So, if it is the input material count is it affects the drafting wave. Multiple input or doubling. If we increase the doubling, then drafting wave will be reduced, and if we have the more number of fibers in the cross section, the irregularity will be low. So, in the draw frame what we do, we use multiple sliver as input. So, to reduce the drafting wave. Roller setting. So, higher the roller setting means there will be more floating fibers. So, that will affect the that will result the drafting wave. Degree of parallelization length and material type. So, this all these parameters, all these factors we will discuss now one by one. So, factors now amount of draft. So, these are the factors. Okay. Now, amount of draft, let us discuss how the amount of draft affect the drafting wave, generation of drafting wave. In case of the floating fiber, so it can be reasoned that the higher the single zone draft, the fewer the number of fibers in the cross section. So, if we have higher draft, here draft is very high. So, suppose here 100 fibers are there, if you are giving draft say 20, so there will be few fibers, 5 fibers will be there. So, higher the single zone, if we give higher draft, so fewer number of fibers in the cross section will be there, and that will be drafted in the ideal way, and therefore, more pronounced thick and thin places will be there, and the greater will be the irregularity. So, what happened in a single zone, if we try to draft single zone and we are trying to draft at the very high rate, then the due to the fewer fibers in the cross section, the generation of drafting wave will be there, okay, thick thin places, and greater irregularity will be there. So, we can see equation here. So, CV output, okay, square is equal to CV in. So, CV square of output material, CV square by input material plus A into draft minus 1. So, where CV input and output material, A is the slope of the line and D is the applied draft. Okay. Now, here you can see this is the slope of the line. Now, from here we can see it is the set draft and here is the relative variance, okay, CV square. Now, if we increase the draft, the in one single zone, the variability increases, because there will be a fewer fibers and it will create thick thin places. So, with the increase in draft, set draft, the fiber that the sliver relative variance, that irregularity increases, and that is same for all the count. So, it is the finer count and it is a coarser count. So, coarser count is also, so there is a straight line relationship, and here thus the CV percent is attributed to be the drafting wave is, this is the A. So, that means what is this? This is due to the drafting wave. Okay. So, input material square plus drafted CV percent due to the drafting wave is A under root A multiplied by D minus 1. So, that is the CV percent due to the drafting wave. So, and here in the drafting system, any spinning system, the CV percentage is added, that is the, it is a variance is added, CV percentage in the square root of CV, square of CV percent, it is added or subtracted, that we will see in next session. Now, A under root A multiplied by D minus 1, that is the contribution of CV% which is added due to the drafting wave. Now, count of input material. Now, if the count of input material increases, so that means it becomes thicker. So, what we can see here, if it is become thicker, so for a particular draft, say draft 5, so if it become thicker, then relative variance will be low. So, if we use the coarser material, so drafting wave, the relative variance, that is the amount of, that is the CV% irregularity will be lower. So, the slope alpha decreases. So, here the slope will be more. So, slope is getting reduced. So, this is alpha 1, alpha 2, alpha 3 slope. So, alpha 1 is more than alpha 2 is more than alpha 3. So, this slope is gradually decreasing. Okay. So, the higher the number of fibers present, the smaller is the value of alpha. Okay. That means, this alpha, this is for coarser, the alpha is reduced and the coefficient of variation of drafting wave also reduced. So, the simple reason for this, that the with more number of fibers present, more fibers will be drafted in ideal way. So, if the fibers are, suppose there are 20 fibers, so there will be few fibers only, say 2 or 3 fibers will be there which will move at the ideal fashion. But if there are 100 fibers, there will be more fibers. So, maybe say 30 to 40 fibers will be there which will move at ideal space, ideal movement will be there. That is why the drafting wave, the CV% or irregularity is reduced. There also will be a greater number of floating fibers, but the spacing between the successive leading ends of floating fiber extent is likely to be more random. So, that will also reduce the relative variance. So, here we can see, now if we see the thick area. So, if there are number of fibers increases, the thick area overlaps with the heavier, overlaps with the thin area in case of heavier count, and thick area, thick and thin area stretched across with the finer count sliver. So, no overlap is there. So, that means, in case of number of fibers are more, that means there is a possibility, probability will be there, thick area is being overlapped with the thin area. So, that will result the reduction in the count CV, okay, the CV%, whereas in case of the thin sliver, during drafting, that chances of overlap is not there. Okay. The sub-drafting wave will tend to be out of phase. So, in case of making thick part in the strip become staggered and becomes alongside the staggered thin part. So, this is the cases where this it is actually stretched again. So, thick plus thick part will remain thick and thin part will be separated. Now, next factor is the multiple input or doubling. So, if we increase doubling like in draw frame, so there will be reduction in the irregularity in the output sliver. So, a multiple input is that is the, this is the advantage of reducing irregularity and entering in the drafting zone such that the coefficient of variation of the entering fiber CV in is reducing. So, with the equation, so input sliver, input material. So, input material is that is a draft in the drafting zone. Suppose there is this is the drafting roller in the drafting zone. Now, suppose we are feeding n number of slivers. Each sliver is having CB, this is the CB of each sliver. Now, total fibers, fiber mass. So, n number of slivers are there, total fiber input CV in equal to CV by under root n. That means, if we the input sliver number of slivers increases as it is becoming high. So, input sliver total CV will be reduced. So, n number of input maybe in the sliver, maybe in other form, and with the coefficient of variation of CV of individual sliver. In addition to reducing the combined irregularity in the input, doubling implicitly has the effect of increasing count. So, it increases the count, okay, and that if we try to reduce by increasing the number. So, the initial thickness, input thickness will be more, which will require the higher draft. Again higher draft will increase the irregularity. So, that effect we have to see, we have to optimize. Thus, during drafting, the drafting wave in the individual input tend to be separately from one another, okay, tend to form separately from one another. And therefore, the equation for reducing the irregularity by doubling also applied to the drafting wave, okay. And thus, with n input each with CV in coefficient variation. So, here the drafting wave will also come into picture. So, that is a CV AO, which is CV AO is actual output, okay. CV output we have seen earlier, CV output equal to CV, that is the actual output is there, that will take care of the draft, okay. Now, degree of parallelization and fiber length and material. Fibers usually have some degree of interlacing when they are not straight and parallel in the input material. So, these are the fibers which are actually in ideal case what we have assumed, the fibers are of same length and they are parallel to each other, there is no interaction between one fiber to another fiber. Now, here fibers are not straight, they are not parallel, they are crossing, they are touching each other, okay, interlacing. The greater the amount of interlacement, the more resistance of sliding past one another. So, here in ideal case there is no resistance, but here as more and more interlacement is there, there will be a resistance of fiber movement and the tendency of for the fibers to be pulled towards the front pair as a clump form, and which results the drafting wave. So, or irregularity. So, this is the if the it is not parallel. So, the fibers in a clump form it will reach to the front roller nip, this obviates the positive effect associated with increasing count. So, with the increasing count, what we have observed, increasing count, the CV% reduces, that is number of fibers increases, but with the increasing count, that means number of fibers in the cross section, there will be many fibers which are not parallel, which are actually entangled, and that will affect the, that will result the thick thin places due to the fibers movement in the clump form. Okay. So, the finer the fibers, the greater the number present in the cross section of the material. So, for fiber fineness, so fiber parallelization we have seen, fiber straightness we have seen, now fiber fineness. So, greater number of fibers in the cross section of the material and more difficult it will be to deal with the interlacing. So, that when the fibers are greater number of fibers, there will be more drafting force and there will be, it will be difficult. Okay. And however, in the drafted material there will be more fibers in the thinner part and consequently the drafting wave will be less pronounced. So, the advantage here is that when we have the finer fiber, in the thinner part also there will be sufficient number of fibers, and that will try to reduce the drafting, that will actually try to reduce the drafting force, drafting wave. The average length of floating fiber group is likely to be increased with the repeated drafting because of the progressive reduction in the amount of interlacing. So, during drafting the interfiber friction tends to straighten and align fibers as they slide past each other. So, that the due to the fibers which are not straightened or aligned due to the interfiber friction, suppose this there is a fiber, now here one fiber is this one which is connected with the back roller. Okay, this is not aligned. So, another fiber which is connected with the front roller. Now, both the fibers are not aligned or straight. Okay. Now, due as this red fiber is moving at higher speed than the blue fibers. So, due to their interaction, interfiber friction, they will try to be straight and aligned towards the axis due to this sliding force and interfiber friction. So, the drafting action removes the trailing hooks preferably to the leading hook. So, the trailing hooks will be removed by the drafting force. Now, reason being that, so here this is the trailing hooks. Okay. Now, at the and these fibers suppose are connected with the back roller. Now, back roller number of fibers will be more because of the due to draft, and in the front roller number of fibers will be less. So, at the back roller the fibers are moving at the slower speed, this is slower speed, and the red fibers which is connected with the front roller it is a faster speed. So, this has got the trailing trailing hook. So, this trailing hook portion is actually interacting with the slower moving fiber which is bluer. So, they will try to pull and the red fiber will be moving at faster rate. So, this hook trailing hook will be pulled and be straightened. So, and the opposite thing, this thing does not happen in case of the leading hook. So, that is why the trailing hooks are preferably removed more during the drafting. Thus, in repeated drafting stage, when the hooks are in trailing direction entering into the drafting zone, more and more fibers will be straightened with their extent becoming equal to the full fiber length. So, now in both side hook, what happened in fast drafting, this is the fast drafting, this trailing hook will be removed. So, this leading hook is remaining, but in the next subsequent drafting this will become trailing hook. So, that fiber, so in the next drafting this will be like this, this leading hook becomes trailing hook, and in the next subsequent process this hook will be removed. So, if we in the subsequently this finally it will become straight. So, that is why two stage draw frame is suggested, where the fibers are the hooks are removed from the both side. Okay, this is removed fiber extent. The associated drafting wave with each repeated stage will be smaller, and if doubling is used in each repeated stage, output will show decreasing trend. So, that is the thing. So, in each stage, each repeated stage, drafting wave generation will be reduced because of the less and less entanglement. So, in the fast drafting stage the fiber entanglements are more. So, the floating fibers move at the randomly, but in the next drafting stage the fibers are relatively straightened and parallel. So, it will try to move at the close towards the ideal stage. So, it will that output will show decreasing trend. Irrespective of the positive effect of fiber straightening, the drafting wave depends on the fiber length and span length distribution. So, where the fiber length is more, the drafting wave will be less. So, and on the particular the short fiber content in the distribution. So, where short fiber content is more, the drafting wave will be generating, okay, due to the floating fibers. And then the roller setting, this roller setting has got, so higher the roller setting there will be drafting wave. So, we will stop at this point. So, next session we will discuss the roller effect of roller setting and how the roller setting is calculated. Till then, thank you.